Alright, it's time for the third video in the stoichiometry series, and this one could be titled Stoichiometry as really used in chemistry. Real quickly, remember that stoichiometry or stoichiometry problems are if-then statements. If I have this much of one thing, then how much of the other thing do I need or will I make? Really important, stoichiometry is mole ratios. Think stoichiometry, think mole ratios. But this raises a problem. There's no direct way to measure moles. There is no instrument out there that you can put something on and it says, this is how many moles I have. But from previous sections, we do know how to deal with this. We know that moles can be counted by weighing, which brings us back to an old familiar equation. Moles times molecular weight equals grams. We will occasionally use this equation, but the vast majority of the time when dealing with stoichiometry, we'll be dealing with moles times molecular weight equals grams. Now this is a very stepful conversion. There happen to be 5 steps. The first is you have to have the correctly balanced chemical reaction. Secondly, you need to figure out what the if-then statement is. Then you need to take the compound that is the if and convert it to moles, and we'll use moles equals grams divided by molecular weight. Then we have to use the mole ratios, which we obtain from the balanced chemical equation, to determine the moles of the then compound, and then we take those moles and convert them to grams using moles times molecular weight equals grams. Now, in all honesty, the best thing to do here is to just jump in and start doing examples, so that's what we're going to do. Supposing you have some lead-2 nitrate. You want it to react with 50.0 grams of potassium iodide. How many grams of the lead-2 nitrate will you need? Well, we're going to figure that out. Step 1, we need the correct balanced reaction. So you have the lead-2 nitrate, potassium iodide. They're going to react. It's a double replacement reaction. And so you end up with these products. But you see you have 1 iodide on the reactant side, 2 iodide on the product side. Ergo, this is not balanced. Use your favorite methodology, and you come up with this being the balanced reaction. So step 1 is done. So the next thing we need to do is to determine the correct if-then statement. If I have 50.0 grams of potassium iodide, then how many grams of lead nitrate are needed? And I put that 50.0 above the Ki and the X above the lead nitrate just to keep track of what's what. I'll explain this more in just a little bit. Step 3, convert the if compound, which in this case is the potassium iodide, to moles using the usual equation. The molecular weight of potassium iodide is 166.006 grams per mole. Take the 50.0 divided by the 166.006 and you get this number on your calculator, but we only want 3 significant figures. So the answer is 0.301 mole, and I write moles under the chemical. Step 4, I need to use the mole ratios to determine the moles of the then product of the lead nitrate. So I set up the ratio, 1 lead nitrate to 2 potassium iodide equals Y over 0.301. Cross multiply, divide, and you get this for the answer. So with correct sig figs, you have 0.151 moles. Now a quick aside, when I'm doing these types of problems, I always write the grams on the top and the moles underneath, and I remember that the stoichiometry is always done with the moles, so always the values that are below the chemicals. That's why you see it this way. So let's go to step 5. We're going to convert the moles of the then to grams. The molecular weight of lead 2 nitrate is 331.2 grams per mole. So we're going to take the 0.151 moles, multiply it by that molecular weight, and you get 50.0 grams with correct sig figs. Okay, let's go to the next example. You got 537 gram sample of dynamite, And dynamite is technically TNT, a trinitrotoluene, and so here's the chemical formula. And it's allowed to explode, and this is a decomposition reaction. Products are nitrogen, carbon monoxide, water, and carbon. And I want to know how many grams of carbon should be produced. So the first thing I do is determine the correct balanced reaction, and the trinitrotoluene becomes nitrogen, carbon monoxide, water, and carbon. Obviously not balanced. Do remember that nitrogen is a diatomic molecule, and so when balanced, it looks like this. I put the 537.00 above the formula for the trinitrotoluene, just to keep track of what's what. We need to determine the correct if-then statement. If I have 537 grams of trinitrotoluene, then how many grams of carbon will be produced? I don't know. So I put an X in the grams place above the carbon. In step 3, I want to convert grams to moles. The if compound is the trinitrotoluene. It has a molecular weight of 227.132 grams per mole. I'm going to use this equation, plug in the values. This is the number of moles that I see on my calculator. So utilizing correct sig figs, I put the 2.3643 moles under the formula for trinitrotoluene. So now we're going to go to step 4. I'm going to use mole ratios to determine the moles of the then compound, which happens to be carbon, represented by the green Y. Set up my ratios. I get Y equal to this after I've cross-multiplied and divided. And so I can write with correct sig figs that I've got 8.2751 moles of carbon. The final step, convert the moles of the then compound, the carbon, to grams, using the old standby, moles times molecular weight equals grams. Molecular weight of carbon is this. Multiply it by the 8.2751, and you get 99.392 grams with correct sig figs. And so I put it there, and I now have my answer. So now, as promised, is a problem for you to do. I'll give you the problem, then I'll show you the answer, then I'll walk you through it, and then we'll review and be done. Okay, you've got an aqueous solution of aluminum nitrate and some sodium carbonate, which made sodium nitrate and solid aluminum carbonate. As a matter of fact, there was 1.23 grams of the solid produced. How many grams of aluminum nitrate were required? Stop, figure it out, come back and get the answer, go. And the answer is 2.24 grams of aluminum nitrate. How did we get that? We started with step 1. We got the correct balanced reaction. So we start with the skeleton reaction, making sure that we have the correct chemicals, and then we balanced it. So here's the balancing. Determine the correct if-then statement. If I have 1.23 grams of aluminum carbonate, then how many grams of aluminum nitrate did we start with? Convert the if, the aluminum carbonate, to moles. The molecular weight of aluminum carbonate is this. So divide the 1.23 grams by the 233.988. You get this value, but we should only have 3 significant figures in the answer. So I write 0.00526 moles under the aluminum carbonate. Step 4, use mole ratios to determine the moles of the then. So the then will be Y. I set up the equation. I cross multiply and divide. I get this value for the Y, 3 sig figs again. So 0.105 moles of aluminum nitrate are required. But the question asks for grams, and I remember that because I have the X written above the aluminum nitrate. So we have this. We go to step 5. We're going to convert moles to grams. So this is the molecular weight for the aluminum nitrate. Multiply it by the moles of aluminum nitrate. You get this value. And so with sig figs, you get 2.24 grams, which is the answer we started with. Okay, to review, stoichiometry is mole ratios. That cannot be stressed enough. It is not gram ratios. It's mole ratios. And for me, that means the numbers under the chemicals. Stoichiometry conversions are very stepful. As a matter of fact, there are 5 steps to follow. The 5 steps are: set up the correct balanced reaction, set up the correct if-then statement, convert if to moles using the moles equals grams divided by molecular weight, use mole ratios to get moles of then, convert moles of then to grams using moles times molecular weight equals grams, and you're done. So that's it for this video. In the next video, we're going to go even more real life, and you'll see what that is in the next video.